Okay, so this is a non-calculator problem. So that means we need to graph these curves without a calculator. So this is a parabola, right? It starts at 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then is this a right side up parabola or an upside down parabola? Upside down, right, because of the negative x squared. Okay, then x squared minus 6 starts down there at negative 6. But it's a right side up parabola. So there's our picture. Okay, so the first thing that really throws people off about these problems is the x and the y-axis have nothing to do with the enclosed region. So do not look at the x and the y-axis when you're trying to figure out what the enclosed region is. So in fact, I'm even going to erase the x and the y-axis and get rid of those, just to emphasize that you ignore those. Okay, so what's the enclosed region then? Kind of this egg-shaped thing, right? We got a parabola like this, and then one underneath it. And so what's getting enclosed is all of that. So our job is to find the area of that. So remember, I said ignore the x-axis. So that means this is not negative area, because it's not below the x-axis. We're ignoring the x-axis. Just all of this region enclosed, we're just finding the positive area of that. So what we're going to do is we're going to draw in some rectangles. So a rectangle here, rectangle right next to it, rectangle right next to it, a bunch of rectangles, right? I don't want to draw all of those rectangles, so just picture rectangle, 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 slicing all the way across this, right? So I'll put one over here. So what the directions in the book say, they say draw the representative rectangle. So they're just saying don't draw all the rectangles, just draw one rectangle that represents all of the rectangles. Okay, so I need to find the area of this rectangle. So I'm going to make up a point here. This is totally inaccurate, but let's pretend that that point is 2, 7. And then let's pretend that this point is 2, negative 3. So this is 2, 7, that's 2, negative 3. Totally making up those points. Those points aren't actually on the curve, I don't think. Just making up some numbers for effect. All right, so if those are the points, what is the height of this rectangle? 10, right? So to get that, you could just take the 7 minus the negative 3. So the height of the rectangle is this y value minus that y value. So in general, I mean, all the rectangles are different, right? So they're all going to be at different points. In general, the height of the rectangle is y2 minus y1. Then the width of the rectangle, we can call it change of x. So this is the height of the rectangle, that's the width of the rectangle. So then when we multiply those together, we're getting the area of the rectangle. So that expression right there is the area of this rectangle here. But we've got a bunch of these rectangles all the way across our bounded region. So we need to add up a bunch of these. So the symbol for adding up a bunch of them is the summation symbol. And let's say we had n of them. So we're summing this from 1 to n. Okay, now the problem with this is just an approximation. Because, let me emphasize a little, let me draw a bigger rectangle here, just to emphasize. If we have a rectangle, there's extra area here that we're getting, right? So if we draw rectangles, we're not exactly accurate in our area. But if we made the rectangles thinner, there'd be less error. And then if we made them thinner again, there'd be even less error. So as we do more and more rectangles, it becomes more and more accurate. So if we do the limit, as n goes to infinity, of that, then that's going to give us the exact area. So there's an expression for the exact area of the enclosed region. Okay, now I haven't really said this in class yet, but you can replace all of this with that. You can think of the integral symbol as an infinite sum, aka it means adding up infinitely many things. So that's adding up, this is adding up finitely many things, but then when you take the limit, you're kind of adding up infinitely many things. So that's what that symbol means. Okay, then, when you go infinitely thin, your rectangle is no longer change of x wide, your rectangle is dx wide. So I haven't said this before either, but dx represents an infinitely thin width. Change of x is a pretty thin width, but it's got some significance to it. But dx is infinitely thin. So then if you go, so this is the height of the rectangle, that's the width of the rectangle, and then you're going to add infinitely many of them up, and that'll give you the area. Okay, now I need to talk about where to start and where to end. So this needs to be my smallest x value, and that needs to be my biggest x value. So over here, in the picture, where's the smallest x value? Right here. That's where the region starts, right? And then the region ends right there. So the biggest x value and the smallest x value have to do with when these two curves hit each other. So now I'm going to do some algebra to figure out when they hit each other. All right, so down here, y equals this, x squared minus 6. So then I can put that in place of y up there. That's called substitution. So I'm taking that, subbing in for y. So then it'll say x squared minus 6 equals 12 minus x squared. So now I've gotten to the algebra portion of the class, right? So in some ways this is the hardest part. Calculus, that's fine, but this is algebra, so is everybody okay with why I'm doing this? Okay, so I'm going to add the 6 over, and that'll give me 18. And I'm going to add the x squared over, and that'll give me 2x squared. And then you divide by 2. And then you take the square root. Be careful, when you take the square root, you get two answers, right? Both positive and negative 3. Okay, so this point right here.
For an interruption, please. I need to see Kathy Park in the attendance office for a minute.
Okay.
Thank you.
So this point right here is negative 3 comma something, right? Because the x is negative 3. And this point right here is 3 comma something. I don't really care what the somethings are, because I just needed to know the x's to start at and end at. So this goes from negative 3 to 3. Okay, then the last thing I need to do is, I can't really leave this with a y, because everything else is in terms of x. So I'm supposed to have x's here and x's here. So if I wanted to find this y value at when x is 2, how would I find it? Plug 2 into the formula, right? Which formula? Yeah, for this curve, that was the upside down parabola, right? So that was the negative x squared formula. So if I wanted to be accurate, I would plug a 2 in there, and I'd do 12 minus 4. So that should have actually been 8. I guess I kind of figured that out. But. Okay, so to get this y value, it equals 12 minus x squared. So I can replace that y value with 12 minus x squared. And then I need to minus the other y value. But the other y value could be obtained by plugging x into the other formula, right? The right side up parabola. So that y value is x squared minus 6. Careful with your parentheses, right? You don't want to just subtract the x squared. You want to subtract the whole thing, x squared minus 6. Everybody still doing okay? All right, so now I'm going to do a little bit of algebra. I'm going to distribute the negative. So that'll be 12 minus x squared plus 6. So then I can add the 12 and the 6, and that's 18. And the x squared give me negative 2x squared. So then I'm going to end up with that integral there. Okay, so now how do you calculate an integral? What's the first step? Find the antiderivative, right? So I've got to find the antiderivative of this. The antiderivative of 18 is 18x. Antiderivative of 2x squared, well, the 2 is just hanging out. Add 1 to the exponent. Divide by the exponent. And then we're going to eventually plug in 3 and negative 3 and subtract, right? So we can remind ourselves to do that by putting in line 3, negative 3. So first step was antiderivative, so we did that. Now we're going to plug in 3. So there's 3 plugged in. Then we're going to plug in negative 3. So there's negative 3 plugged in. And then we're going to subtract. So 18 times 3 is 54. Right here, that's 27. Divided by 3 is 9. And then 2 times 9 is 18. This is negative 54. And plus 18, because that'll come out to negative 18, but it's minus a negative 18, so it'll be plus. So then we've got 54 minus 18 plus 54 minus 18. So that's 108 minus 36, so 72. So what did we just find? Area of that egg-shaped looking thing, right? And apparently 72 is the answer. So what that means is area is in little squares, right? So that means 72 of those squares would fit inside of that enclosed region. All right. So let's try another one. How about find the area of the region enclosed by y equals x squared and x equals y squared. So still trying to go non-calculator. So y equals x squared is a parabola facing upwards. Just starts at 0, 0. That looks like this. Now for the other one, I'm just going to be careful and practice. If you're not sure, because one of the things that's hardest for you guys is to graph without a calculator. So if you don't know how to graph something, you can always just plot points. So for this one, we're just going to plot some points. The equation is kind of backwards because it says x equals y squared. So I'm going to pick some y's to plug into the equation. So -2, -1, 0, 1, and 2. The point I'm trying to make here is, if you don't have a calculator, you don't know what the graph looks like, you can always just find some points and then see if you can connect them in the correct way. So here the x equals the y squared. So if I take -2 squared, that'll give me the x. So that'll be 4. And then -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So now I can just take these and plot them over here. So 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. So it ends up being a sideways parabola, which isn't surprising because if y equals x squared is a right side up parabola, x equals y squared should be a sideways parabola, right? So where's the enclosed region? It's that little part here, right? So I'm going to draw that bigger so we can see it better. So bigger, that would look like this. So I'm trying to find that area. So the directions in the book say draw the representative rectangle. So here is a representative rectangle. There's rectangles going to be drawn all the way across that. We're going to find the area of a bunch of them, but it helps us to draw one of them so we can kind of picture what's going on. Okay, so to get the height of that rectangle, you'll take this y value minus that y value. So the height of the rectangle is y2 minus y1. And once we go infinitely thin, which we're going to do, right, the width of the rectangle will be dx. So we have the height of the rectangle times the width of the rectangle, and then there's going to be infinitely many of those to add up. Isn't that crazy? I say, oh yeah, then we're going to add up infinitely many of them. And I put this symbol down, and you guys are all like, oh yeah, we'll add up infinitely many of them. If I'd said that before calculus, you would have said I was crazy. Well, you still say I'm crazy, but you're okay with adding up infinitely many things. That's a big deal, right? We're just casually saying, oh yeah, add up infinitely many of them. We can do it. Okay, so then I need to figure out what this should be and what that should be, right? Well, we have a dx here, so that means these need to be x's. So we need the smallest x value on the shaded region and the biggest x value on the shaded region. Well, the smallest one is right here, and the biggest one is right there. That point is 0, 0, obviously. What's this point? I didn't make it super obvious what that point was. It's 1, 1. Does everybody see why it's 1, 1? Because in both equations, 1, 1 works, right? 1 squared is 1. Okay, so then this should be from 0. Now, this is going to be silly, but this 0, not that one, right? We're talking about the x's. So here it's a coincidence that they're the same number, but it's that 0 that I care about. And then to that 1, not that one, this 1. Okay. Because I'm just saying that because on another problem, this might be different than that, and you're going to use that number. Okay, so now we got to decide this y value here, that's y2, right? That y value goes with which curve? X equals y squared or y equals x squared? Yeah, that curve is x equals y squared. And this curve is y equals x squared. So the bigger y value comes from this curve. So the smaller y value is x squared, right? Because y equals x squared on that curve. So the reason I'm translating this to x's is because everything's supposed to be in x's. dx, x's, so this, I can't have that. So the y equals x squared. Now for the other equation, I don't know what the y equals because they told me what the x equaled. So I have to do some algebra to solve for the x, or solve for the y. So I'm going to square root both sides, and I get y equals positive negative square root of x. So if you graph this with a graphing calculator, if you graphed the positive square root of x, you would get this. And then if you graph the negative square root of x, you would get this. And then you'd get your full sideways parabola. So this curve is what? The positive square root of x, right? Because it's the top half of the parabola. There's the bottom half. Okay, so it's the positive square root of x that goes there. And we're going to integrate that from 0 to 1. Okay, so now we got to do the antiderivative, plug in 0, 1, and subtract. Before we do the antiderivative, just keep in mind that another way to write the square root of x is x to the 1/2. Yeah?
Would there be a point in time where it would be like both the positive and the negative side?
I think you could get an enclosed region that would include that curve minus that curve, yeah.
So what would we do?
Take positive square root of x minus negative square root of x. Okay, so now the antiderivative of this, you got to add 1. So x to the 3/2 divided by 2, or divided by 3/2, which is the same as timesing by 2/3, minus x cubed divided by 3, which is the same thing as timesing by 1/3, and then from 0 to 1. Then you plug in 1, so that's 2/3 times 1 to the 3/2 minus 1/3 times 1 cubed. And then you plug in 0. And then you subtract. This time when you plug in 0, it comes out to 0. That's not going to happen every time. There's some functions that you can plug 0 into and not get 0, right? For example, if it was cosine. Cosine of 0 is 1. So don't just assume that since you're plugging 0 in, it's going to come out to 0. This time it happened. Then this is 2/3 minus 1/3. Because 1 to the 3/2 is 1, 1 to the 3. So final answer is 1/3. So apparently, this little bitty area here is 1/3 of a square. Because area is always in squares, right? So it's 1/3 of a square. Okay, so those were non-calculator problems, but now we're going to do a calculator active problem. So you can get out your graphing calculator if it's not already out. So we're at example 3 here. And the curves are y equals 2 cosine of x, and y equals, I think it's x squared minus 1, but I better double check. And we're finding the area of the region enclosed by these curves. Okay, so first thing you want to do is go to your y equals. So press y equals. And then type in 2 cosine x. Squared minus 1. then you got to set your window. -3 to 3, and for x, and -2 to 2 for y works well. Then you press graph. It was -3 to 3 and -2 to 2. Everybody doing okay? All right, so then which one's on top? The cosine one, right? So 2 cosine x is on top. So that's the bigger y value, since it's the one on top. So to get your, you're going to take 2 cosine of x minus x squared minus 1. Careful of the parentheses, right? Then, so that's the height of your rectangle. Then you multiply that by the width of the rectangle and add infinitely many of them up. Now we need to find these values, right? How will we find those? Those are the intersection points of the 2 curves, right? So you do second, calculate, second trace. So make sure you practice this. So do second trace, which is and then down to 5 for calculate intersect. Now, when you move your cursor, just go left and right. Don't go up and down. So go to the left until you get to the intersection point. And when you get pretty close, press enter. And then it wants you to press enter again. You don't really need to move usually, but if you do move, just go left and right. Don't go up and down. So then it'll give you that first intersection point. It's -1.265424, and then 0.60129.716. Everybody getting that? Okay, you did all right back there? All right. So which of those values do we care about? The x value, right? Because it's dx. Everything's in x's. So -1.265424 is my, now what should I round that to? You'd be tempted to say 3 decimal places, right? Because that's what I keep saying, 3 decimal places, 3 decimal. The problem is, this is the middle of the problem. And if you round to 3 decimal places in the middle of the problem, it might throw off your 3rd decimal place in the final answer. So I would put it all down. I'd put -1.265424 down. I think this is a symmetric graph, so I think the other x is going to be positive 1.265, but I think we should practice. Yeah, so intersect that other, calculate the other intersection point, because this calculate intersect thing so what is this number? Negative 1.265424, is that right? And then when you get the other one, it's 1.2654237. Isn't that interesting that the reason why you're getting an extra decimal place is because it's not having to use a screen place for the negative sign, so it has space for an extra place. I assume this was also 37, but it rounded it to 4 because that's what it had space for. Because it's a symmetric graph. It is an even graph. Okay, so now what? Just math 9 this, right? So math 9, type these in, do that. Watch your parentheses. I mean, I'm going to put in x squared plus 1. And then I don't have to worry about that extra set of parentheses in there. But if you put in x squared minus 1, you better minus the parentheses of it, right? Find the screen off. The problem is it won't focus on this. Okay. So you get 4.995. Rounded to 3 decimal places. So that's the calculator. Everybody doing okay? Got it now, Grace? All right, awesome. So now we're to example 4. Too much stuff here. So we're going to find the area of the region R in the first quadrant bounded above by x equals y squared, below by the x-axis, and y equals x minus 2. So find the area of the region R in the first quadrant bounded above by x equals y squared, below by the x-axis, and by y equals x minus 2. Okay, so I mentioned that earlier that you were supposed to ignore the x-axis, and usually you do. But on this problem, they're telling you not to ignore the x-axis. It says that the x-axis is part of what's bounding your region. So unless they specifically say use the x-axis or the y-axis, then you do ignore it. It's not part of the bounded region. Okay, so we already graphed x equals y squared earlier. That looked like this. And y equals x minus 2 would be a straight line. Y-intercept negative 2. So the thing that's confusing about this problem is the bounded region is this. If you just look at the two curves, the bounded region is all of that. But they're specifically saying only that in the first quadrant and also include the x-axis. So if you draw in the x-axis as well, then you get two bounded regions, right? But they're asking specifically for the one in the first quadrant. The easiest way to do this problem is to do this. So I'm just going to find all of this area and then subtract out that triangle. So this area here is just an integral underneath the square root of x. And then it's going to be 1/2 BH. Getting towards the end here, so I'm rushing a little bit. Is everybody okay? Are you sure? How do I find this point here? Intersection between this curve and this curve, right? So x is y squared. So I could put y squared there. So y equals y squared minus 2. So the y values are 2 and -1. Ah, look, there's two intersection points, right? Which is the one we want, the 2 or the -1? The 2, right? Because that's a positive y value. But we need the x, which is 4. So this would be 0 to 4. So I'm not going to be able to finish this problem, but that's okay. I think you can find the area of a triangle. Have a good one.